The Cold War was in many ways a battle of technology, the East and West competing for the technical edge by building bigger, faster, and more powerful weapons. It was a time of fear and paranoia, with military strategists on both sides probing each other and themselves for potential weaknesses. The United States Air Force, now in the jet age, struggled with the dilemma of defending its airfields along the Iron Curtain. A sneak attack might cripple their fighter bomber force and their ability to launch a tactical nuclear attack. At the same time, the Soviets were concerned with defending themselves from an American bomber invasion. But how could they wholly defend the borders of their vast territory? Both sides would look to the past to safeguard their futures and solve these complex problems. Pushing technology, they developed systems for launching and landing aircraft which might have seemed out of science fiction. It was a struggle to free aircraft from their dependency on runways and to achieve a zero-length launch. "1953 was a tumultuous year in the Cold War. Though an armistice brought hostilities to a close in the Korean War, the arms race continued to gain momentum on both sides of the Iron Curtain. The Soviets tested their first hydrogen bomb in August of 1953, equaling a feat accomplished by the US just a year earlier. For the next 3 decades, both sides would continue to construct and stockpile more deadly atomic weapons. Fleets of aircraft were assembled to deliver these strategic nuclear arms, and there was a continuous pressure to build aircraft that could fly higher, faster, and carry even bigger bombs.
They were on 24-hour alert during those early days of the Cold War, 1948, 49, 50, 51, 52. Most people do not know how precarious that period of time was. The Russians were out to do it. They would have done it.
The consequences if either side dared to deliver a single strategic nuclear weapon were learned in Hiroshima and Nagasaki. But if a military conflict broke out between the US and the Soviet Union, could an all-out nuclear war be avoided? The US was also prepared for a smaller-scale war, with tactical nuclear weapons. These weapons allowed each side to strike devastating blows to key targets without necessarily escalating the conflict to a full-blown nuclear war. All along the Iron Curtain, NATO aircraft sat ready to deliver such weapons. However, no matter how fast or technically advanced the aircraft or powerful a weapon it carried, each one had the same Achilles heel: runways.
How many airfields did we have in Western Germany? And I'm only talking about the RAF. The runway is really the home of probably 30 aircraft. Taking out the runway, if there are airplanes on the ground, now they can't get out. And if you're looking to put down somewhere because you're running out of fuel, you can't get in.
Attacking an enemy's runways was not a new strategy. During World War II, the Axis and Allies both tried to cripple their foes' air forces while they were helpless on the ground, as well as impede any remaining aircraft from taking off and landing. In the early 1950s, damaging an enemy's runway might have been particularly effective, as jet technology was still being perfected. Jets were underpowered, thus necessitating longer runways during takeoff, particularly in hot conditions or at higher altitudes. But safeguarding the runways from aerial attacks was not the only anxiety of NATO's military planners. There was also a possibility of their airfields being overrun by a Soviet ground invasion.
There's no doubt that the Russians would attack with tanks. Where are you going to put your airfields that are not invadable by a heavy tank force? They are where they are. The idea for the Russians was to move forward, overcome the forces, grab their airfields, and start operating out of those airfields.
The vulnerability of its airfields, and therefore air force, to an aerial or ground attack was a concern for NATO. But there were no ready solutions. That is, unless there was some way to free aircraft from their dependency on runways. The origins of one answer to the runway dilemma can be traced to World War II. The Me-321, or Gigant, was a massive German glider designed to carry armored vehicles, equipment, and troops to the front lines in Operation Barbarossa. With a fully loaded weight of almost 76,000 pounds, a lengthy runway was a necessity to say the least. Launching the Gigant proved problematic, even with multiple aircraft serving as tows. What was needed was additional thrust. To provide the extra power needed to launch this behemoth of an aircraft, the Germans turned to rocket power. Even before the war, Germany had experimented with rocket-propelled aircraft, like the HE-176. Rocket engines, like the one in this vehicle, function by combining two chemicals together in a combustion chamber to produce a violent reaction.
Two liquids were used in the engine, a C chemical and a T chemical. They were put in separate tanks, brought together by pumps inside the engine, and once they were mixed together, you didn't need any ignition, they went.
The resulting hot gases are expelled out of the rocket at high pressure and high velocity to propel it forward. Looking for a solution to boost the Gigant, rocket pods utilizing this chemical technology were affixed under the wing. During takeoff, the pods provided the Gigant with 30 seconds of thrust, just enough additional power to allow the heavily burdened aircraft to take to the air. Although launching the Gigant in this way proved to be an unwieldy solution, and it did not eliminate the need for a runway totally, it did at least shorten the required length, and was therefore a step in the right direction. The Germans continued to experiment with RATO, or rocket-assisted takeoffs, during the course of the war. The RATO 234's underpowered engines necessitated a lengthy runway, sometimes difficult to find under wartime conditions. Like the Gigant, rocket pods were affixed under its wings to facilitate a shorter takeoff. Perhaps the pinnacle of German rocket-assisted technology was the Bachem 349, or Natter. The Natter could launch vertically with the aid of a rocket engine and rocket boosters, thus totally eliminating the need for a runway during takeoff. These innovative aircraft were built for point defense, defending German factories and military sites against the relentless Allied bombing assaults.
It was, in a way, for me, the precursor of the space shuttle. It took off vertically. It had booster rockets, which were ejected when they had been spent. It had a task to do, which was really to deal with the bomber formations that were massing over Germany at that time, and then would come back to Earth. The pilot would eject. The aircraft itself will come down in two parts with two drogue chutes, and can be reused.
Though the Natter did not proceed past the testing phase, it did provide the template for a fixed-wing aircraft which did not rely on runways. After the war, U.S. aircraft manufacturers took up where the Germans left off, continuing to experiment with rocket technology. Solid rocket boosters were affixed to underpowered jets and other heavier aircraft to facilitate a shorter launch. But could rocket technology eliminate the need for runways altogether? A U.S. Cold War project called ZELL sought to answer that very question. ZELL, an acronym for Zero-Length Launch and Matte Landing, envisioned launching the U.S.'s fighter bomber force almost vertically in the air with the aid of powerful rocket boosters.
Tactical Air Command requirements people came up with the idea that to protect aircraft on bases in Europe from surprise attacks and so on, to help them provide survivability, it would be a good thing if they could disperse the aircraft around the perimeter of the airfield. But then the question was, well, if you got them dispersed, what does it take to get them launched and get them together and so on? So somebody came up with the bright idea that we could shoot them off the back of a truck with a rocket-assisted boost, why we could just take off from where they were, buried in the woods someplace.
The scientists and engineers at Martin Aircraft were entrusted with developing the ZELL launch system. Their experience with the Matador missile made them a logical choice for the project, as their cruise missile was launched in essentially the same way planned for ZELL. Both systems made use of mobile launch platforms and powerful rocket boosters. Once rocket power was exhausted, a jet engine served as the primary power source to propel the missile, or in the case of ZELL, the aircraft, to its destination. The Matador was a descendant of another piece of German World War II technology, the V-1 or buzz bomb. This early cruise missile was shot into the air via a rocket-powered catapult. Although the V-1 lacked a jet engine, it did have a pulse engine, which propelled it as it traveled across the English Channel. Testing of ZELL was to consist of 3 phases: unmanned launches, and manned matte landings. On December 15th of 1953, at Edwards Air Force Base, an EF-84G Thunderjet was ready for the initial phase of testing. Stripped of all unnecessary weight and married to a 57,000-pound thrust T-50 rocket, it soared across the desert sky in a brief moment of glory. The sacrificed Thunderjet would pave the way for manned launches in Phase 2 a month later. Martin test pilot Robert Turner was selected for the first flight. Strapped into the cockpit of his Thunderjet, he revved up his Allison J-35 engines to 100% RPM. The aircraft trembling, he fired his rocket booster. Though jolted by the initial Gs, Turner was soon flying comfortably. He returned to base victorious, having earned a spot in history as the first man to successfully execute a zero-length launch. Now that it had been proven that ZELL aircraft could take off without runways, a second problem still remained. How do you return them to base? In the case of the Natter, the German solution was to devise an elaborate parachute system to recover the fuselage and pilot. However, the Natter, constructed mostly out of wood, was more than 5 times lighter than the 11,000-pound Thunderjet. Parachutes just wouldn't be practical. Another possible solution was thrust reversers. By blocking the flow of its engines, a jet can be made to operate almost in reverse.
If you're faced with long runways to get your airplane airborne, when you come back to land, you've now got to stop the thing. Well, you obviously couldn't have barriers and wires on an airliner or even a transport airplane. You'd tear it apart. So the idea was, could we turn the thrust of an engine and reverse it to give you at least a partial reduction in your landing distance? And the answer to that is yes.
Though they shortened the required runway length during landing, thrust reversers did not totally eliminate the need for runways, and were therefore a partial solution only. The British also toyed with an alternative means of landing an aircraft. During World War II,
the big advantage that it offered by having an undercarriageless aircraft was the undercarriage on an average naval aircraft is 7% of the all-up weight. So if you remove that 7%, you can replace it by fuel, ammunition, or whatever. And so you've got that to play with. But also, because there's no undercarriage, you can stow them in the deck on layers above each other, and you could double your fighter complement on a carrier.
to return an undercarriageless aircraft to its carrier, British engineers constructed a rubber deck to soften the landing.
The rubber deck was in fact a sheet of rubber which was rather like made of what you would call the outer cord of a tire. And instead of having a large number of arrestor wires to land on, you had one wire, but it was not lying almost flat like on the deck. It was lifted up about 3 feet on 2 stays and draped across. You had only the one, and the idea was you flew into it. You didn't do a landing like you throttle back and then flop onto the deck. You just flew into this wire, and if you caught it, you flopped it down onto the deck.
Experiments were carried out with modified de Havilland Vampires. Program test pilot Captain Eric Brown
We did 200 landings in all on the ship, and I made all the initial ones so we got the installation as we wanted it, and then we handed it over to 4 pilots who were chosen from being below average, average, and above average, and 1 American. And let them all have a go, and we had no problems at all. The whole thing faltered, of course, because of the logistic problems. If you have a problem and you can't land on the carrier and you have to go ashore, or you have to go ashore for maybe regular maintenance, every airfield you're likely to go to must have a rubber deck installation on it. So that was a logistical headache. And of course, if you're twice the number of fighters, you've got to have a lot of supply ships with you to feed the fuel and etc. to them.
A similar rubber mat system was conceived for the ZELL tests. The Goodyear Tire and Rubber Company was put in charge of building the mat, as well as installing a Navy arresting gear mechanism at the test site at Edwards Air Force. Phase 3 of the program commenced on June 2nd of 1954. Turner was once again in the cockpit. This test, however, would end with disastrous results. While trying to catch onto the arrestor wire, his F-84G inexplicably bounced off the rubber mat, damaging his aircraft beyond repair and breaking his back. The crash was a setback for ZELL, but a temporary one only. The defects corrected, Phase 3 testing resumed 6 months later. Gliding over the Goodyear runway, Rodney had better luck than Turner. His tailhook system functioned almost perfectly. Though a triumph for the program and Rodney, his success was short-lived. On December 11th, he tried to repeat his accomplishment, but this time his F-84G bounced violently onto and along the mat, causing him severe injuries. The ZELL system had proven it was possible to rocket launch an aircraft without a runway, but the rubber mat landing system was just too erratic. The search for a system to launch and land fixed-wing aircraft without runways did not die with Rodney's December 11th flight. ZELL had been born out of a fear of a Soviet sneak attack on NATO's runways and infrastructure. Ironically, the Soviets took up where the Americans had left off. The Soviets were well aware of the growing fleet of U.S. nuclear bombers. However, their Air Force could shield selected targets only, given the vastness of their territory.
They had lots of airplanes, which you're then going to have to pick the major targets, and we could be sitting in this room for a week deciding whether that target was more valuable or more important than that one.
To maximize the spread of their shield, a launch system was proposed, similar to ZELL, which would allow interceptors to operate from remote locations. In place of the Thunderjets, the Soviets fired off reinforced MiG-19. Testing between 1956 and 1957 proved successful, but the project was still cancelled. The plan had many drawbacks. It did not eliminate the need for a runway. The Soviets intended to land on shortened runways by deploying brake parachutes. As well, it was difficult to transport the launch platform. Furthermore, in 1957, the Soviets unveiled the S-75 Diva surface-to-air missile. The Soviets positioned hundreds of these SAMs around populated areas. The SAM was not the only technical achievement of the Soviets. 1957 also saw Sputnik go into orbit, initiating the space age. The Soviets seemed to have the upper hand technologically, and with their silver satellite roaming freely high above American skies, some were left feeling vulnerable. Perhaps as a response to the Sputnik launch, or growing Cold War tensions, the USAF reopened the ZELL file. This time, however, they planned to fire off nuclear-armed F-100 Super Sabres. Brigadier General Robert F. Titus recalls his own test flights.
They elevate the airplane to about 20 degrees nose high, and then you run it up, check out the engine, put it in full burner, and then you pull the trigger and you're gone. Well, it was transverse 4Gs, so it pushed you back in the seat pretty hard, but it was a 4-second burn, and now you're at 275 miles an hour.
Returning the aircraft to base was still a problem. Mat-assisted landing had proven unworkable in the original ZELL tests, but there were no new alternative landings. If no runways were available, it was suggested that pilots could sacrifice their aircraft and bail out over safe territory. The tests were for the most part successful and reinforced the viability of launching aircraft via rocket. Though ZELL was technically feasible, employing it operationally would create complications.
The problem with it logistically was that how do you get your continuation training when you got the airplanes scattered about the perimeter of the airfield on launchers? You got to have training. Guys have got to go out and requalify in gunnery every 6 months. Then maintenance is a problem. You got these airplanes elevated on a truck bed, and maybe you need them in the hangar, so moving them back and forth was a problem. Then finally, in my estimation, although no one had told me this, I always felt that, well, security is a problem. I mean, you've got these things scattered about, you need an awful lot of armed guards around the perimeter then.
ZELL proved an all too costly and complex solution. The final Super Sabre was launched on the 26th of August, 1959. For the next 3 years, the Cold War continued to intensify. Gary Power's U-2 was shot down by a Soviet SAM. Berlin was divided in half by a wall. And the world narrowly escaped a nuclear disaster. In 1963, concerned with the vulnerability of their own runways to attack by Eastern Bloc countries, the Luftwaffe began their own experiments.
Well, if you think about it, the Allies and the Russians were prepared to fight a war on the German landscape. So they were going to be at the center of this no matter what, just because of their geographic situation. So the idea whether you could influence the battle by having lots of rapidly climbing aircraft to take out the bombers before they got over your territory is obviously a dream come true.
As was the case in all previous ZELL systems, their plan was to disperse their aircraft into remote areas, making it much more difficult for enemies to knock out their entire force. To recover their planes, they considered using any runways which had survived attack. The Luftwaffe chose the Lockheed F-104G Starfighter for experiments carried out at Edwards Air Force Base in California. The system once again proved to be viable, and in 1966, the tests moved to Lechfeld, Germany, where 2 wings of these aircraft participated in further trials. Though ZELL and ZELL were abandoned, the vulnerability of NATO's runways remained. New technologies emerged to answer this concern, including aircraft capable of VSTOL, or vertical short takeoff and landing, aircraft like the Harrier or jump jet. By redirecting the flow of its engines downward, the Harrier can take off and land vertically without the need of a runway.
The Harrier looks like a fantastic solution. Very big engine, doesn't carry a lot of fuel, and it doesn't need a big massive airfield to support it. But what people don't realize, if you're 30 miles from the front line, wherever that is, and you've got 8,000 pounds of ordnance on your airplane and 20,000 pounds of fuel, so where are the trucks? Where are the fuel bases to support that? That means a squadron of 24 airplanes could get rid of humongous amount of weaponry and fuel. In fact, The Harrier could only go to war in Europe alongside a railway line, because you needed a train to supply that amount of ordnance.
Another solution to the runway dilemma, born out of zero-length launch technology. The Matador missile, which inspired the ZELL launch system, was a precursor to future advanced guided missiles. Such weapons make it possible to strike enemy sites with tactical nuclear weapons without ever launching an aircraft and risking the life of a pilot. Relatively cheap, mobile, and accurate, ZELL and ZELL were innovative solutions to a complex problem. Scientists and engineers developed interesting potential answers, pushing technology in new directions. Experiments by the US, the Soviets, and the Luftwaffe all came to the same conclusion. ZELL and ZELL were simply not logistically practical. It would take a fresh approach to finally free aircraft from their dependency on runways and allow armed forces to strike, defend, and operate in secluded locations, minimizing the risk of a surprise attack.
I have always admired the US Navy with the way they use aircraft carriers. And I was at Farnborough at a very exciting time of carrier innovation, where we evolved the three major things. Firstly, there was the steam catapult, which could throw heavier aircraft off at much higher end speeds and with much less adverse acceleration on the pilot. In other words, with the normal cordite catapult, you went off, there was a colossal bang and you were a shock and then you were thrown off. With the steam catapult, you accelerate up to the max, so a max G. So it's quite comfortable. But the end result is wonderful. You get tremendous speed at the end, and you can take off much heavier weights. So that was a big innovation. And of course, it's using the ship's steam as the source. Secondly, of course, and above all, was the invention of the angled deck. Now that came about as a result of experiments done on what is called the flexible deck. This is landing an undercarriageless aircraft on a rubber deck. And we had a problem with getting the aircraft off the rubber deck in time to land on the next aircraft. So, ideally, you wanted a clear landing lane and a clear parking area, rather. And during conversation, while we were discussing this in general, the chairman of the meeting, who was a captain in the Royal Navy, happened to make a doodle on a piece of paper showing going off at an angle. But it didn't occur to him. It must have occurred to him, but he didn't process it any further to the meeting. He just, left it. But sitting opposite him, thank God, was the head of the Naval Aircraft Division at Farnborough, who saw this, and it clicked with him immediately. This is a practical solution that could be actually incorporated in a carrier. That's how it evolved. And I was just about my time just after leaving Farnborough. The Americans had asked if I could go to America, to their test center, Patuxent River. And the farmer said, well, take the drawings and the details of the angled deck to them, and that'll be a nice introduction for you. And that's how it was. And of course, they were delighted and seized on it, and as only the Americans can do, worked with lightning speed to get it to be a practical idea. I had been in the jet flight, and it was all very top secret at this time, and the then boss of the outfit said to me, look, he was very interested in the Navy. I always had a good rapport with him. And he said, you know, you should be thinking of getting one of these onto carriers. And I said, well, can I have a look over the stable to see what we've got? And there were 4 jets at the time. There was the E-2839, the Gloucester, our first jet, and there was only one left. So this was ruled out because it was really an engine test bed. There was the Meteor, which was twin-engined and really too big for the job. There was the Bell Aerocomet, the American one, which we didn't want to touch because it was sluggish and it was their aircraft anyway. And then they left us with the only other alternative, which was called, at that time, the de Havilland Spider Crab, which became the Vampire. So that it was almost, if you like, Hobson's choice. And we selected that. The Vampire was a very, very docile aircraft, easy to fly, and all handling characteristics, very benign. So I thought there is no problem there at all. The only problem we had was at that stage in jet development, the acceleration of the jet engine and the deceleration was very poor. For example, it took on the aircraft that were fitted with British and German engines and American, all at that time we were all suffering from the same problem, slow acceleration. For example, the Meteor took 15 seconds to go from zero idle to full power. Now, in a deck landing, if you suddenly need more lift because you've let yourself get too slow, you need instantaneous lift, which you get from a piston engine aircraft with air screw. And throttle is... So what we wanted was throttle reaction on a jet like you have on a piston engine. That was inevitably coming, and in fact it only took about 9 months to come after we did the first landing. But our big boost to all this was we were going to beat the Americans to it, which we did by 9 months.
During the early stages of the Cold War, and before the advent of guided missiles, the West had to rely heavily upon jet-powered fighters to ward off Soviet bombers. For some time, the only effective armament for these fighters were barrages of unguided missiles.
One of the changes that took place in the 1950s involved air-to-air weapons. It had been traditional until then that combat airplanes would carry machine guns or cannons. And everyone knew and everyone said that fighters need guns, except when they didn't say that. And they didn't say that when they were talking about defending the United States against bomber attack. They designed several types of interceptors that used partly or entirely unguided air-to-air rocket projectiles.
At first, each interceptor would just have one opportunity to fire in a gunshot approach with a weapon from a bygone war. The B-29 was more expensive to develop than the atom bomb. It was so complex to build that some manufacturers are said to have taken on other projects just to avoid being selected to assemble this most advanced flying machine. Even Boeing didn't really want the task of building their own creation. In the end, the Army Air Force took over much of the management, although Boeing, Bell and Martin still had to deliver. The B-29 was cloaked in secrecy throughout its early development. Occasionally details were released, but this was really disinformation to confuse the enemy, who by 1944 had seen enough of the superfortress to fear its destructive capability. In one such subterfuge, a single B-29 was landed near London to convince the German High Command that many other B-29s were to follow. The result was that Germany took extensive precautions to counter the superfortress, although none were necessary as the United States never planned to attack Germany with B-29s. The war against the Japanese Empire was a very different matter. Japan was the target that the superfortress was conceived and built to attack. Rushed into service, many early B-29s flew over Japan with technical problems, particularly with engines overheating. One safe haven for a damaged and struggling superfortress was the Soviet port of Vladivostok. At this time, Russia was not a combatant with Japan. In fact, it was technically a neutral power that could not give support to either the United States or Japan. At least 3 B-29s were forced to land in Vladivostok. They were promptly seized, repaired, and flown to Moscow. Just before the Japanese surrendered, Russia declared war on Japan, which made them a US ally in the Pacific. But Russia still refused to return the 3 B-29s. American wisdom was that a superfortress would be technically too sophisticated for Soviet engineers to replicate. And that view prevailed for several years, even as the Soviet relationship deteriorated from ally to enemy. However, in 1947, at Moscow's annual Aviation Day parade, 3 B-29s appeared overhead. At first, Western observers assumed they were American, but opinion quickly changed when a 4th identical aircraft appeared. Soviet engineers had obviously developed a clone. This was bad news on the aviation front, but worse still was the knowledge that the Soviets had for some time breached Western security and had gained access to atomic secrets. The Los Alamos project alone had at least 3 Soviet spies in its workforce. In August 1949, the Soviets, in an exercise known as First Lightning, detonated their first atomic bomb. The news shocked the West. Soviet possession of the atom bomb and the means to deliver it demanded an effective response. However, most Western air forces at the time were still flying fighters from World War II. Anticipating the nuclear threat, in 1946 a new air defense command had been formed for the aerial protection of the continental United States. At first, the ADC had to rely upon a stalwart Second World War night fighter, the Northrop P-61 Black Widow. The aircraft offered some radar capability, long-range and all-weather endurance, but most important of all, it was available. Later, an unusual derivative of the successful P-51 Mustang, the P-82 Twin Mustang, was pressed into service. The original P-82 was envisioned as an escort fighter. It was fitted with radar and served as an ADC interceptor. However, neither of these aircraft had the speed of a jet, and they relied upon machine guns or cannons, neither of which were likely to be very effective against a B-29, wherever it was built. Having designed the superfortress in the first place, the US knew only too well its defensive capability. The task of successfully downing a B-29 had been given to German engineers some years earlier, when the Nazi hierarchy were tricked into believing that superfortresses would be used over Germany. The Wehrmacht's answer came in the form of the A4M rocket. The rocket had been developed from an artillery missile of slightly less than 3 inches diameter and had 8 folding fins. These would be fired in a salvo at an oncoming American bomber. The salvo approach was necessary because the rockets lacked accuracy. Allied intelligence had been aware of the A4M's devastating effect when they hit a target, especially when coupled with the speed of an Me-262. Against this arrangement, the Allies had no answer.
One of the weapons that really, I think, would have been a very frightening thing if it had gone much further was the Me-262 armed with the R4M rocket missiles. Now, they had 2 batteries or 2 racks of 12 in each wing, and they were used right at the end of the war. Not in a great deal, but when they struck a bomber, it wasn't a question of damaging it or downing it, it was a question of disintegrating the entire thing. It was, a hit was total destruction.
The technology was really quite basic. In the 262's case, the launch platforms were basically carved out of wood. Other German interceptors using the A4M were fired from a simple metal tube nicknamed the stovepipe. Apart from the A4M's motor, the only other technology it employed was its folding fins, which snapped open after launch. FW-190s and Me-262s were adapted to use Germany's new rocket defense. However, there was one aircraft that was built around the A4M. Extremely ambitious and reflecting the desperate state of the Third Reich, the Bachem-Natter's sole reason for existence was to deliver the deadly folding fin rocket. The Natter used a chemical-driven Walter rocket as its main motor. 4 solid-fueled rocket power plants aided its vertical takeoff. Bachem's design only flew on 1 occasion and killed its young pilot in the process. But knowing of its deadly potential, Allied ground troops were to prioritize the capture of anything to do with the A4M. Fast forward to 1949. NATO gives Russia's clone nuclear bomber the codename Bull. By this time, some of America's first-generation Air Defense Command jets were close to delivery. Many of them were developed for use with 2 valuable assets that would help reduce the Soviet threat. Firstly, the US had improved on the A4M concept with the introduction of a 4-finned 2.75-inch rocket that would ultimately be named Mighty Mouse, after the popular cartoon character of the time.
Quite a few of the aircraft projects in the 1950s did away with the gun. It was thought the gun, and in other words close-in fighting, was no longer required. It would be air-to-air missiles. But you can only carry a small number of missiles at a time. And so an alternative to the gun was the unguided rocket. In America, the version was known as the Mighty Mouse.
Airborne radar was also coming of age. First employed at the end of World War II, it was now ready for use in conjunction with ground radar. Radar was particularly important when employing fighters known as interceptors, as they are required to fly at night and in all weather conditions. In 1945, the US Army Air Force was preparing to enter the jet age and had asked for submissions for a jet-powered night fighter to replace the propeller-driven aircraft it then had in service. A serious contender for this contract was the Nighthawk, a four-engined dual-seat interceptor from the Curtiss-Wright Company. The Nighthawk's failure to perform in flight tests in 1948 led to the demise of the Curtiss-Wright Company. Instead, Air Defense Command chose a contender from Northrop. The F-89 Scorpion had two engines for safety and dual seats, one for a dedicated radar operator. The Scorpion was to be equipped with cannons because Mighty Mouse was not yet available. Delays in delivery of the F-89s had the advantage of enabling them all to be fitted with folding fin rockets. In fact, the Scorpion could carry 102 of the rockets.
The F-89, which was quite an interesting aircraft with big rocket pods out on the end of the wing, and pretty heavy aircraft, but the usual case that we've done in so many of our aircraft, by the time we get through hanging things on them, they're all underpowered. and the F-89 didn't last long, but it was one of the airplanes in the air defense development that took place as we moved into the Cold War time frame and our expectations that we might have to fight Russia.
However, late delivery of the F-89s at this very sensitive time in history led Air Defense Command to order two other interceptors as immediate backup. Lockheed calculated that they could convert the T-33 trainer to a two-seat interceptor using up to 75% of the Tu-33's parts, a major saving in money and, more importantly, time. ADC was very impressed as the first flight of the XF-94 was made just 3 months after the contract was signed. The latest C version of the Starfire carried Mighty Mouse rockets just as they were starting to become available. The second backup for the Scorpion was a North American aviation project. The company's F-86 Sabre had been a major step forward in fighter design, but it was primarily a dogfighter, not an interceptor. But North American believed that the basic frame could be converted into the interceptor role. In the event, only about 25% of the original F-86 parts were used to make the F-86D or Sabre Dog. Nevertheless, their unit cost was around 1/3 of the twin-engine Scorpion. Nearly all the 2,800 F-86Ds that rolled out of North American's plant were armed with the Mighty Mouse rocket. Like the Nazis' Bachem-Natter interceptor rocket, it existed solely for the purpose of delivering 2.75-inch folding fin rockets.
The F-86D didn't have any guns. The F-86D Sabre carried a tray of these rockets under the pilot. The tray had to be extended, then the rockets could be fired.
There was another interceptor that would be armed with the folding fin projectile, the Canadian CF-100.
We had 2 rocket pods, 29 rockets each, and so there's 58 total, and it was a one-shot effort. So when you were into a bomber stream and locked onto the bomber, you would fire these things off, and it was essentially a shotgun type approach. You're bound to hit something. One rocket would do the job.
Of course, it's all.
Canada's Arctic region required an all-weather aircraft. Like the Scorpion and the Starfire, the CF-100 had a two-seat configuration with a dedicated radar operator in the rear. Working in conjunction with a string of early warning radar posts, almost 700 CF-100s were built. They served for almost 30 years. So important was the project that Avro Canada cancelled its promising early jet airliner design to concentrate on its rocket-firing defender of North America. Eventually, Mighty Mouse rockets were superseded by supersonic surface-to-air missiles like the Boeing Bomark. Army Nike shorter-range anti-aircraft missiles took over much of the air defense role in the mid to late 50s. Air Defense Command did retain the use of some Mighty Mouse rockets on its new generation interceptor, the F-102 Dagger, but only as support for the Falcon guided missile, which was the Dagger's primary weapon. As guided missile technology improved, the Mighty Mouse was no longer able to compete for a spot on board US interceptors.
The unguided rockets, they didn't have very much range, they were unguided, and of course the moment you fired them they were under the effect of gravity, so actually getting them to accurately hit a target, anything beyond a very short distance, was really not much chance. And so needless to say, by the 1960s this weapon wasn't carried very often at all.
During the Vietnam War, the 2.75-inch rocket was paired with armed helicopters, and it was reborn as a ground attack weapon. Literally millions of Mighty Mouse rockets were launched against North Vietnamese targets from a wide range of US rotary and fixed-wing aircraft. Specialized warheads could be fitted onto the rockets depending on their intended end use, be it anti-personnel, anti-tank, or basic target marking. During the Gulf War, the Apache helicopters that opened the air campaign by destroying 2 Iraqi radar sites with Hellfire missiles also carried Hydra 70 rockets, the modern-day incarnation of the Mighty Mouse. The folding fin rocket was born out of the Reich's desperate need to stop the flow of Allied bombers devastating its territory. When faced with the possibility of nuclear annihilation by Soviet bombers, the US grabbed onto this German weapon and adapted it into their own Mighty Mouse. Those surface-to-air missiles and air-to-air missiles would relieve the Mighty Mouse of its intended mission of knocking down Soviet bombers, the folding fin rocket would find new life as a ground attack weapon, a mission it still carries out to this day.
.163, as I said, was a tool of desperation with a poor operational record, and I consider its contribution to aviation was that it had so many innovatory features on it. But strangely enough, at the end of the war, it was the aircraft that influenced world aviation thinking more than any other unit. The ME-262 is a great contribution again, quantum jump in performance. It took us into a new era of high speed. It was a beautiful airplane to fly, but it had very, very sensitive jet engines, and they were temperamental. And when they were acting correctly, you had a great airplane on your hands. When they were temperamental, you had quite a difficult airplane on your hands. Ju-88 was outstanding aircraft. As I described the 3 top British, the Germans had 3 top ones. These were the Focke-Wulf 190, the Ju-88 and the Messerschmitt 262. JU-88 was asked to do a multitude of things, many, many roles. It excelled in every one of them, and in one form was actually faster than Germany's fastest fighter, piston engine fighter, let's say. So I had the highest respect for it.
The takeoff problem of military aircraft is one which vitally affects the performance, utility, and efficiency of the United States Air Force. In order to attain the maximum possible speed, range, and payload that could be achieved in each aircraft model, the runway lengths have been continually increased. In some cases, high aircraft gross weights have dictated runway lengths exceeding those economically feasible. The solution to this problem is to provide additional thrust during takeoff. A study conducted by the Engineering Division of the Air Materiel Command has indicated that, compared with other methods of providing auxiliary thrust, rocket power plants have several outstanding advantages insofar as performance and logistic considerations are concerned. When a B-29 with a heavy gross weight of 140,000 pounds takes off, there are two factors that tend to increase its length of ground roll. To the B-29 pilot, these two factors seem like giant hands, pressing downward to retard his ground speed and ability to become airborne. The factor most variable is temperature. Takeoff in climates having temperatures ranging from sub-zero up to 120 degrees Fahrenheit is experienced throughout the world. At any given elevation, sea level for example, the length of ground roll of a B-29 increases with temperature. At 0 degrees, the bomber with a gross weight of 140,000 pounds rolls 4,960 feet before the wheels leave the runway. When the temperature rises to 30 degrees, the length of ground roll increases to 5,280 feet. With the mercury registering 60 degrees, the distance grows to 5,600 feet before the aircraft becomes airborne. When the thermometer shows 90 degrees, the ground roll extends to 5,890 feet from the start. Test data show that at 120 degrees, the heavy bomber will not become airborne in less than 6,220 feet. These figures on ground roll during takeoff are the results of the effective temperature only, and show that the higher the temperature, the longer the ground roll. Now for the other factor, elevation, starting with the runway at sea level. With ground roll distances as affected by temperatures established, any variance of runway elevations above sea level tends to further increase the length of ground roll. At an elevation of 3,000 feet, the ground roll lengthens to 6,950 feet. At 5,000 feet elevation, the distance increases to 7,450 feet. These effects of temperature and elevation on the distance required for takeoff of heavier and heavier high-speed aircraft created a complex problem for engineers at the Power Plant Laboratory at Wright-Patterson Air Force Base. A specific requirement was to reduce the ground roll of the B-29 with a gross load of 140,000 pounds to 1/2 that normally required. Solution and necessary equipment were to be supplied as quickly as possible. Rocket power was the accepted solution. Urgency of the requirement, coupled with other performance requirements, indicated a modification and utilization of existing equipment. After due consideration of propellants and current designs, a power plant was designed that would produce, when used in multiples, sufficient added thrust to meet shorter ground roll requirements. Following the design and performance specifications stipulated by AMC power plant engineers, a contract was awarded to the Aerojet Engineering Corporation of Azusa, California, for manufacture of liquid propellant rocket power plants for use on bombardment-type military aircraft. This rocket power plant consists of 3 cylindrical tanks which contain pressure gas, fuel, and oxidizer respectively, a thrust chamber assembly, control panel, cowl, valves, and associated plumbing. The components of the rocket power plant are assembled to form an integral unit in a structure that provides attachments for installation of the rocket power plant beneath the wing of an aircraft, and which also includes means of transmitting thrust from the rocket power plant to the aircraft. One of the first steps in production line assembly of the rocket power plant is the installation of the forward bulkhead on the air pressure tank. The control panel is added. This panel is installed as an assembly with the lines connected and contains a pressure regulator valve, a pressure line valve, and the solenoid control valve. The pressure tank is rotated at this point to expose the bottom side of the control panel, and the following controls are identified: oxidizer tank vent valve, fuel tank vent valve, pressure regulator valve, pressure tank fill valve, pressure tank gauge, and the pressure line safety diaphragm. The thrust chamber assembly is next mounted on the power plant. An aluminum oxidizer tank is installed on the assembly by means of 2 bulkheads. The fuel tank is then added. After the rear propellant tank straps which hold the propellant tanks in the assembly are attached and tightened, a red fuel tank restrainer cap and a green oxidizer tank restrainer cap are installed over the ends of the tanks. After the installation of the thrust chamber assembly, the propellant lines and joints are inspected. Coming around to the front end of the power plant, an aluminum cowl designed to reduce aerodynamic drag covers the regulator and control valves. The propellants used are a mixture of xylidine and gasoline as fuel, and red fuming nitric acid as the oxidizer, which when coming in contact with each other react spontaneously, thereby producing the high temperature gases which are the source of the rocket's energy. In the field, the power plant is transported on a modified M5 utility trailer to the fuel servicing cart where fueling takes place. Here the aluminum cowl is removed to permit access to the tank filler caps. All valves are checked to ensure that they are in closed position. The fuel filler cap is then removed. This cap is washed in water to increase safety in handling. Vinylite acid-proof clothing, rubber gloves, and boots are worn during servicing. The hood is equipped with a respirator suitable for operation with nitric acid fumes as well as xylidine gasoline fumes. A flexible servicing hose is removed from the stored position on the fuel cart, and the filling nozzle adjusted to the rocket fuel tank. A gasoline motor supplies power to the pump on the servicing trailer, and the amount of fuel delivered to the power plant is determined by a level indicator in the nozzle, which is controlled by a portable switch. When this operation has been carefully completed, the servicing hose and nozzle is replaced on the fuel servicing trailer. Future designs of servicing equipment will minimize any fuming or leakage of fuel or acid. Water is used as a flush. The rocket power plant is next moved to the acid servicing trailer, and the same procedure used for servicing the acid tank. As in the fueling process, the filler cap of the acid tank is removed. The hose is adjusted. The acid nozzle is installed in the acid tank and locked in. The servicing complete, the cowl is replaced and the completely serviced unit is moved to the test firing range. Two standard Mark 8 bomb hoists are used to install the rocket power plant on a mock-up of a typical aircraft installation, where it is then test-fired. 4 men can install a loaded unit in approximately 10 minutes. Attaching the high-pressure air hose is the last phase of servicing the power plant before firing. The shock waves in the supersonic exhaust gases can be readily observed. The duration of firing is 45 seconds. At the end of the firing, the blow-down operation is carried out, resulting in dense fumes being emitted from the thrust chamber, as can be seen here. This provides for the purging of the complete propellant system after firing. We now come to the actual installation of 4 rocket power plants under the wings of a B-29 at Muroc Air Force Base, California. The servicing procedures used here are similar to those already demonstrated in the mock-up test firing at the Aerojet range. Upon locking the rear mounting lug in the S1 shackle on the airplane, the sway braces are tightened hand-tight. The power plant electrical control wire is then attached to the wing outlet with a quick disconnect fitting. This view shows the position of the 4 rockets as installed on the airplane. The 2 tank vent valves and the pressure tank fill valve are checked to ensure that they are properly closed prior to attaching the high-pressure airline. Then the high-pressure airline valve and the pressure tank fill valve are opened. After the pressure has reached 2,500 pounds per square inch, the valves are closed. Ground inspection of the rocket power plants is made prior to takeoff to ensure they are properly installed, the electrical connection secure, and the power plant controls correctly positioned. The rockets are then armed by opening the pressure regulator valves, and the power plants are now ready for firing. A ground crew specialist advises the pilot that the rockets have been armed. The main engines are started, and the B-29 taxis out for takeoff. In this case, the rockets are turned on 10 seconds after the brakes are released. The B-29 gross weight on this takeoff was 148,000 pounds, including the weight of the loaded rockets, 2,000 pounds each. A 25-degree flap setting was used. The ground roll was 2,900 feet. At Muroc Lake, where the runways are 2,280 feet above sea level, the temperature was recorded at 60 degrees Fahrenheit during takeoff performance tests of the B-29. Loaded to a gross weight of 140,000 pounds, the B-29's minimum ground roll without rockets was found to be 6,000 feet. When the thrust force of 16,000 pounds was added for takeoff, the same aircraft was able to shorten its ground roll to 2,900 feet before the wheels left the runway, a decrease in ground roll of 3,100 feet. With the successful completion of the assist takeoff tests, the rocket power plant has now been completely tested and delivery made to the using agency. To show the advantage of rocket-assisted takeoff for increasing payload without increasing ground roll, an analysis has been made of the B-29 flight test results and is here presented in animated form. The maximum takeoff gross weight of a B-29 without rockets is 110,000 pounds for a fixed ground roll of 3,000 feet. A B-29 loaded to a weight of 140,000 pounds, plus the addition of 4 rocket power plants, including propellants, weighing 2,000 pounds each and giving an additional thrust of 16,000 pounds, makes a gross weight of 148,000 pounds, which may be taken off in the same ground roll distance. This gives an increase in payload of 30,000 pounds, or 27%. But the assisted takeoff program is not complete. The problem has been solved for a single type of aircraft. Now, different propellants, turbine pumps, new materials, more efficient injectors, safety controls, and internal type installations all contribute to more efficient and economical assisted takeoff rocket power plants for other military aircraft.
Major tests will establish that over on a very steep approach angle to simulating and landing in mountainous terrain or in a hostile environment. Demonstrating the short field landing capability, they will touch down and immediately reposition the propellers to full aft, stopping the aircraft at just 1,500 feet. You will notice not only can the aircraft stop quickly, it can actually taxi backwards.
And we'll be taxiing into position, and in just a few moments we're going to hand over the microphone to Blue Angels. Last call for flash pickup. Please look around you, the box seats around your area. If you see anything lying around loose, please pick it up and look at it by transfer. Please pick up.
Hi, my name is Lieutenant Commander John Allison, Blue Angel number 5 and lead solo pilot for the United States Navy Blue Angels. My dad had a small airplane and it just got me very, very interested in it. You know, obviously he would let me fly a little bit and I just liked it. I was attracted to it from the start. Started taking some lessons from him. He was an instructor. I just loved it, absolutely loved it. I got my pilot's license before my driver's license actually. What's impressed me the most about this team is that the level of teamwork, the level of professionalism basically eclipses anything that I've ever seen. These guys are great. For me, it's a little slice of America. But I feel that anybody can do this. It doesn't matter where you come from. It doesn't matter what your background. If this is what you want to do, you can do it. And that's why I fly airplanes. That's why I fly for the Navy, and that's why I do what I do. Because if one kid walks away from this show thinking that he can do something he didn't think was possible, then we did our jobs.
The Blue Angels have been around since 1946. 61 years ago, Admiral Chester Nimitz knew that the Army Air Corps was becoming the Air Force, and he wanted to make sure that Congress kept spending for naval aviation. Therefore, he tapped on the shoulder of a young lieutenant commander, a war hero, a fighter ace by the name of Roy Butch Boris. And back then, he started the Navy Flight Demonstration Squadron that we now call the Blue Angels. Another thing that most people don't know about the Blue Angels in our demonstration is the fact that we do not fly with G-suits. The G-suits are kind of like the blood pressure cuff that you get at the doctor's office, except it's around your calves, your thighs, and your midsection to help you fight the Gs. The computers help you think along with the jet. So as Gs are pulled, that blood is kept up in your upper half of your body, closest to your brain. So the reason why we don't wear G-suits is very, very simple. If you're dogfighting, it's very unpredictable. There's a lot of heavy G loads, and you just can't process that information fast enough. So the computers on board the jet will inflate and deflate your G-suit to help you along in that process of dogfighting. On the other hand, our demonstration is very, very finely choreographed. It's the same maneuvers. It's on that roller coaster track. The same demonstration that we do week in and week out becomes very familiar to the pilots. So they know the onset of G is coming. They know how to fight it, and they're working well in advance of the maneuvers. The problem is with the stick right between their legs, they use their arm as a fulcrum on their thigh, and there's a 40-pound spring on that jet for inverted flight. So it's like sitting in a chair in your room with the 40-pound dumbbell doing this for 48 minutes. That tends to take a lot of energy out of your arm. So to compensate, they use their thigh as a fulcrum. When they do that, if they had G-suits on, the bladders would inflate and deflate as they were taking G, which could cause PIO, or pilot-induced oscillation. So the stick could be bumped by their wrist, which is bumped by the air bladders. And that is actually less safe than flying without the G-suits in the first place.
I came to flying late in life. And to me, the lessons, the life lessons that one learns when you accept the responsibility of piloting aircraft are the most valuable lessons. It was work. It was, it's amazing, an amazing experience.
I think it's really important for everybody to understand that the average F-18 squadron has about a dozen jets and about 250 to 260 people. The Blue Angels have about a dozen jets, but we also have a C-130. We have 110 people. And when we go on the road, we take about 7 jets with us, depending on the show site. We also take Fat Albert. And oh, by the way, we have the oldest F-18s in the Navy and Marine Corps, and we only take about 50 enlisted personnel with us. So for every hour that a jet flies, we can expect somewhere around 20 to 25 man-hours of work to go into this jet to make sure that it's ready for the following air show. In some cases, we may need parts, and Fat Albert may have to go make a late run. But by and large, the next day, you can expect a full lineup of jets. And a testament to our troops and what they've done. In 61 years, we've never had to cancel an air show due to maintenance inavailability of our aircraft.
Oh boy, I was, as a kid, I was an aviation nut, and it was only when I started racing cars when I was about 15 and a half that I kind of got away from it. But I got my pilot's license when I was 17. I always dreamed of being able to fly in the military. Jack's been an unbelievable influence on my aviation career, I guess. You know, he's really allowed me to go out and do the things I want to do in aviation, and he's facilitated some things and taken me up in his jet, and he says he's going to give me a ride in his P-51, but he's taught me a lot flying along. I don't know if you've ever flown with Jack, but he's a heck of a teacher, and you know, he'll only tell you once, and then he'll yell at you when you forget, but he makes an impression, and he's a great guy and a great aviator. The flight we just took was unbelievable. It's unbelievable. I just can't describe it. You know, the whole event's amazing. It's an amazing aircraft, and the things that Kojak, Kevin there could do with it were pretty spectacular. He almost got me unconscious. He got me to the point where I didn't care. That was pretty close.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.
With America and the Soviet Union engaged in a massive arms race, both sides are eager to acquire the technology that will give them a distinct advantage over the other. Bombers, missiles, nuclear-powered submarines and satellites launched into space are all highly sought after during a period where the entire world could be obliterated with the flip of a switch. During this weapons race, Nazi scientists are brought over to both sides of the curtain, where the weapons that at one time were to be used against them are studied and developed further in order to produce a checkmate against the opposing power. The names Werner von Braun, Walter Dornberger and Hermann Oberth are usually mentioned when this topic in history is discussed. For it is their work that gives the United States the X-15, a rocket-powered plane that reaches the edges of outer space and holds the world record for speed, flying at over Mach 6. The X-20 Dynamic Soarer, a futuristic space plane that is to be used for multiple purposes, including the bombing of the Soviet Union from outer space. Designs demonstrating America's commitment to be the undisputed champion of Cold War weaponry. And while the names von Braun and Dornberger are etched in stone as the architects of American ingenuity, there is another scientist who is often overlooked by writers and historians. His name is Dr. Jürgen Sanger, a brilliant theoretician who has bigger dreams and aspirations than all the others combined. His ultimate goal is to produce a hypersonic spacecraft that can take passengers around the globe in mere hours. He has a concept that Nazi Germany desires to convert into a lethal weapon to be used against the United States. An idea that is resurrected from the ashes of the Second World War to be used as a game changer for whoever can master its concept. This is the story of Dr. Jürgen Sanger, one of Hitler's spacemen. The story of Jürgen Sanger begins at the turn of the century in the nation of Austria, where as a young child he is infatuated with the idea of man landing on the moon. Like many others from his generation, the idea of space travel galvanizes Sanger, who reads as much science fiction as he can acquire during his impressionable youth. One book in particular that captivates Sanger is Hermann Oberth's Die Rakete zu den Planetenraumen, or By Rocket into Planetary Space, a prolific blueprint of ideas.
He read the books by Hermann Oberth and all the other space travel books. Most of them were science fiction, but that's how he got interested in space travel, going to the moon, going to Mars, and beyond.
There was a lot of great scientists there, with fantastic ideas, futuristic ideas. I mean, even Werner von Braun, who did the V2, I mean, his ideas were way ahead of anybody else.
Studying civil engineering at the University of Technology in Graz, he acquires his PhD in what would now be called rocket science. Sanger is a true rocketeer who, like others, must adapt to the new regime that is taking control of Germanic lands. During a period of intense military build-up, where Austria would soon be incorporated into the Third Reich, Sanger begins work on his magnum opus, a high-speed transport plane called Silbervogel, or Silverbird.
It was his idea in the 30s, mid to late 30s, to build a high-speed passenger aircraft that could fly from Berlin to Tokyo in a matter of hours, or fly from Berlin to New York City in a matter of hours. It had nothing to do with a military aircraft. It had nothing to do with a suborbital rocket bomber. So the Silverbird started out in Eugen Sanger's mind as a high-speed, high-altitude passenger plane. It's almost similar, I guess the idea would be similar to the Concorde.
When you watch a rocket, when you watch a Saturn V or any rocket take off, you notice it takes off slowly and gradually gathers speed. Well, this is because the most energy in that is involved, more energy than any other aspect of that flight is involved in takeoff. So if you could find a way to make that ramjet, this huge ramjet engine and this huge bomber, take off without using any onboard fuel, you'd really have something there.
There was a debate among the German and Austrian rocket enthusiasts about whether you would use a pure rocket to launch you into space or whether you would use some combination of the airplane and the rocket, using a winged vehicle. So his Silverbird was an idea that he had, was one of many iterations of an idea for this kind of hypersonic or even orbital rocket plane.
It is a revolutionary concept. A vehicle capable of taking passengers from Berlin to Tokyo in mere hours by bouncing off the Earth's atmosphere.
Gravity would eventually want to pull it down. And so what Sanger would do, he'd fire up his 100-ton rocket engine, and he would dive down to about 25 miles altitude, where there's a very dense layer of atmosphere. Now, once this aircraft hit that dense atmosphere, it would bounce off of that, and it would be reflected back up again. It'd be like a child throwing a flat stone across a lake. It bounces along, skipping along. That would be the same principle for Sanger's Silver Rocket.
Eugen Sanger developed a concept where you would launch a bomber, a manned bomber, into the stratosphere, into the high reaches, near reaches of space. And then you would re-enter the atmosphere and bounce back up and bounce back down, up and down. And they calculated that you could easily circle the world doing this with their 20-ton thrust Sanger ramjet engine.
While Sanger is not a man of war, his nation is on a path to war.
With all of these guys, you face the same issue, that they are space enthusiasts, but they're also nationalists. They're also, in cases, quite Nazi in their beliefs. So there was no contradiction between their space enthusiasm and being asked to work on rockets as weapons. They saw, on the one hand, rocket weapons, whether it be rocket plane or pure missile, as duty, contribution to the nation, contribution to the Third Reich. At the same time, they saw it as a stepping stone to going into space. So they really didn't see much of a contradiction, if any, at all, between the two.
And very soon, Hermann Göring, the head of the Luftwaffe, a man who will be responsible for Germany's aerial arsenal against the Allies, begins to take a serious look at the possibility of turning the Silbervogel into a deadly state-of-the-art weapon.
The Third Reich was only interested in weapons. The space ideas are all very nice and exotic, but they funded Sanger, they funded von Braun and others because they wanted weapons. They were out to conquer the world, and they needed the weapons to do it.
Although the United States presents itself as a neutral nation, their President Franklin Roosevelt is sympathetic to the nations of England and France. And as the 1930s come to a close, it is almost inevitable that America will enter the war one way or the other. Unfortunately for the Nazis, there is no available aircraft in their arsenal capable of reaching the United States and back to deliver a fatal blow. By 1939, the best means available is Germany's U-boat fleet, who, when given the call, will engage in unrestricted submarine warfare against America's shores. Traditional aircraft, known as the America bombers, are being designed and built on the fatherland during the war, but remain a giant question mark in terms of range and payload. In a country with a fascination for wonder weapons, spending enormous sums of money on ideas and concepts that in the end may not be realistic at all, it is only natural that Zanger's grand vision is given the green light by German war planners.
When he started working for the Luftwaffe in the late 1930s, I think he looked for a way to sell this idea. The Silver Bird was supposed to be a skip bomber, a hypersonic vehicle that would be launched probably from a sled. It would go into a suborbital trajectory, and it could extend its range around the world by essentially skipping off the atmosphere like a rock.
A group of rocketeers are organized and funded by Goering, with research and development to be done at the Hermann Goering Institute, located north of Hanover.
Hermann Goering was involved in rocketry, and he saw what the Army was doing with the V1, the V2, and he said, "Hey, I think I should be involved in this as well." So he started his own group of rocketeers, men who he could find who hadn't been picked up and picked over by Dornberger.
So he started to invent and manufacture power plants, and these were in rocket and pulse jets. And from that, he also designed mini fighters with pulse jets, which then led to the idea that perhaps, we could actually go into the atmosphere and have long distances and bomb United States or whatever.
It is there where Zanger and his future wife, Dr. Irene Brett, a brilliant mathematician, begin working on the Silbervogel. On paper, the aircraft is to be launched from a 2-mile-long sled track where rockets will push the Silverbird to over 5,000 feet in altitude.
The Germans decided to use this to put a little vehicle behind this Sanger ramjet bomber that was just tied to the sled, to the electronic sled, and it would push this Silverbird off into the air at a good clip.
He'd have a 2-mile-long monorail that would be pushed along by probably 2-3 dozen of Werner von Braun's V2 rocket engines. At the end of the monorail, the aircraft is going almost 1,200 miles an hour. Once it reached that speed, it would take off at about a 30-degree angle and go up to about 80 to 90 miles altitude.
When the aircraft's power plant ignites, over 600 tons of thrust is generated in a mere 11 seconds. Climbing to over 130,000 feet, the target for its 1-ton payload are the cities of New York and Washington, D.C. Traveling at hypersonic speed, no existing Allied plane or anti-aircraft artillery can touch this Silbervogel on its voyage halfway across the world. After releasing its bombs, this futuristic aircraft will hopefully land on either Japanese territory or on the deck of a U-boat submarine. It is a grand concept, a project that requires years, if not decades, of research and development and vast sums of money in order to complete. Ironically, one of the Silverbird's biggest flaws comes from Zanger himself.
He had a habit, when he ever come up against a problem which he couldn't solve immediately, he would move on to something else. So consequently, Sanger investigated a lot of things, but he jumped around. He jumped from one idea to another, to another, to another.
In studying its design, those in the top German hierarchy have many questions surrounding the aircraft's rocket engine.
With the Silverbird being rocket-powered, there's no plan B for it. Once you ignite the engine, it runs until it runs out of fuel, and you have to. It takes you wherever you have to go, and that's the end. With the supersonic transport, like the Concorde or the SST, I mean, you can turn, you can land, you can refuel, but you could not do that with Sanger's Silverbird. And so, feasible, yes; practical, no.
Also, legitimate concerns are raised about the project's feasibility in a time of war.
The hypersonic vehicle requires an incredibly a difficult exotic metal structure in order not to melt. And then you would have the trajectory problem of skipping off the atmosphere is difficult, not impossible, but very difficult. So essentially it was a completely utopian concept for the Third Reich.
This thing flies so high and so fast that how would you even drop the bomb knowing where to drop it and where it's going to hit? For example, the Silverbird, if it went around the world, and that's what it was designed to do, leave Berlin, fly around the world, and on the opposite pole would be New York City. You'd have to drop the bomb somewhere in Iowa. Iowa to New York City is a long, long distance.
He is a visionary, but not a practical man. While the V-1 flying bomb and the V-2 rocket are thoroughly tested on Peenemünde during the war years, the Silverbird is never able to get past the drawing board.
But it was all really fantastic futuristic ideas which in today's world could be realised. But they were so far ahead of their time that Germany didn't have the capability in terms of facilities, equipment, the technology even was still only on the drawing board. And it would have taken a lot of experimentation to actually realise the ideas.
I mean, this was a paper proposal, and I think in so many of the enthusiast, Nazi exotic weapons concepts that the enthusiasts love, have failed to see just how beyond the technology of the time. I mean, it would be a difficult thing to carry out today, let alone in the 1940s.
By 1942, with the war going in Germany's favor, the Silbervogel is cancelled indefinitely. As the Third Reich faces attacks on two fronts, cuts need to be made, and an enormously expensive space plane is one of them.
Around 1941-42, the Luftwaffe lost interest in this whole utopian project of Zenger, because Zenger wanted to scale up his effort to build a major rocket engine and so forth for his airplane. And that was beyond the ability of the Luftwaffe to commit, especially as the war situation got more and more difficult. And there was essentially a contradiction between spending a lot of money on Zenger for rocket development when there was already a huge rocket project in Germany, the von Braun Peenemünde project.
With the Silverbird's termination, Zanger and Brett are assigned to work on developing ramjet technology for the fatherland. The aircraft appears to be all but dead. 3 years after the project's cancellation, Germany surrenders to the Allies. With both sides closing in from the east and west, Nazi scientists who worked on the Third Reich's wonder weapons become highly sought-after bounty. In the United States, Operation Paperclip is enacted in order to bring these men to America to begin work in their own defense industries. The same people who developed the deadly V-2 rocket that killed thousands during the Second World War now have their slate wiped clean as they begin their new lives, working for their one-time enemy. With tensions escalating as the Soviet Union becomes America's biggest adversary, they will need every advantage possible in order to defeat a regime that soon will possess both the atomic bomb and a delivery system capable of reaching the cities that Germany could never touch. Surprisingly, while hundreds of scientists are rounded up and sent to both sides of the Iron Curtain, Zanger and his wife, Irene Brett, go to neither superpower. Instead, they travel to France to restart their failed research.
Anybody who was picked up by the Soviets post-World War II, for example, if Zanger had been picked up by the Soviets, he had been squeezed like a lemon in order to get whatever knowledge and technology ideas he had out of him. He didn't want to go to the Soviet Union. Now, Zanger did not want to come to America in Operation Paperclip. In fact, he was never invited. Zanger was that small group of scientists in Nazi Germany who felt betrayed that the Americans had beat them, had defeated Nazi Germany, and that they were still mad, still angry with the Americans. And so Zanger, along with a few others, said, I'm not going to work for the Americans. I will not go to America. I'll go to France, where there's a more friendly work environment, and that's where I'm going to continue my career.
With the Soviet victory in 1945, its army begins capturing detailed blueprints of numerous German designs being worked on during the war.
When the Soviets overran Berlin, they overran the Reichsluftfahrtministerium building, and they copied every aircraft design that the Germans had proposed and were proposing to build post-World War II. They had all of these documents translated into Russian, so they knew every aircraft that Germany was working on or was thinking about in the future.
One plane in particular catches the eye of Joseph Stalin.
Stalin seized upon the idea about 1946-47 and was interested in funding it, and because it seemed like the magic answer to figuring out how to attack the United States.
The Soviets wanted Sanger. The Cold War was starting, and they thought, well, maybe one day we're going to have to bomb America, or maybe one day we'll have to bomb Australia. Maybe one day we'll have to bomb any other country around the world. Now, according to the documents that we have here, Sanger's suborbital rocket bomber could bomb any location in the around the world. So they said, Stalin says we got to find Sanger.
The Silver Bird, with all of its unique advantages on paper, appears to be an ideal weapon to use against the United States. And for that reason, he orders a Soviet espionage team headed personally by Stalin's son to kidnap Sanger and bring him to the Soviet Union. The attempt fails miserably.
Well, Sanger was tucked away in France, and although Vasily Stalin could travel all over Europe, he was more of a playboy. He'd go to Paris, and he enjoyed the ladies of the night. He drank heavily, and so it got to the point where he was more interested in the cities he visited and the enjoyment he found than finding Sanger.
It is suspected that the communists lose interest in Sanger's ideas, as they discover in the same way that German scientists did that Sanger's plane is unachievable. On the other side of the world, where interest in spaceflight is reaching all-time highs, German scientist Walter Dornberger, who now is working for Bell Aircraft in Buffalo, New York, attempts to recruit Sanger, the same man who Dornberger criticized as a hopeless dreamer.
There was fascination in the United States with Sanger's Silverbird concept hypersonic flight rocket planes in the 1950s specifically.
His crowning achievement can be seen in America's X-20 Dinosaur, incorporating a similar principle to that of his Silverbird design. A revolutionary spaceplane built during the Cold War, it is ultimately cancelled in 1963 due to both money and logistical problems. What becomes the beginning of the end for Iogan Sanger is his decision to go to work for Gamal Abdel Nasser and the Egyptians, developing missile technology. When it is discovered that an ex-Nazi is working for an Arab nation to defeat the Israelis, he is dealt a fatal blow to his career.
For a short time in the early 60s, he was kind of part of a scandal of, old Nazis and working on rockets for the Egyptians against the Israelis.
He was secretly working for Egyptian President Nasser, helping him design long-range missiles that could be fired at Israel. Well, the Israeli Secret Service found out about this, and Sanger's lucky he was never assassinated by these people because they were ruthless. Well, anyway, Sanger was alleged to be earning $500,000 a year from President Nasser. And word got back to Germany, German officials, and they didn't know what to do about it. Now, Germany at the time, West Germany, was seeking admission into NATO. And they didn't want any kind of conflict. They didn't want any kind of thing that was embarrassing. They wanted a smooth transition. So they decided that Sanger had to go.
Sanger would spend his final years in exile, dying in 1964.
I had talked with Sanger's son, Hartmut Sanger, several years ago, about this time when he was fired by the German government. Sanger lost all interest virtually in his work, didn't publish, didn't write, didn't speak. he ended up being a broken man, and Hartmut Sanger, his son, said that what had happened to him was the cause of his early death at 59 years of age.
In summing up the career of Jürgen Sanger, one can describe him as a utopian visionary, unable to turn his ideas into something concrete in the same way Wernher von Braun was able to do with the V2 rocket.
Well, Sanger is certainly an important visionary of the 1920s and 1930s, with some influence on future concepts for hypersonic flight on rocket airplanes, reentry technology. He has influence. He's not technologically, little of what he did actually played out in something familiar that actually got built.
His inability to see things through would relegate his career to that of a theoretician, unable to capture the headlines the same way his colleagues were able to. At the same time, his contribution to rocket technology, to ramjets, to the lifting body, to skip trajectory, and to hypersonic flight can never be ignored. Had his Silver Bird been completed, its impact would have been monumental to whatever country possessed the weapon. For that reason, Dr. Jürgen Sanger, one of Hitler's spacemen, is in the history books as one of the most brilliant minds of the 20th century.